Let me remind you where we are. So Maria's doing, or yesterday Maria did perfect graphs. That's assuming you have a graph with no odd hole and no odd antihole. It's a complement of an odd hole. Then prove that the chromatic number equals clique number. But today what I want to talk about is conjectures of Jarfash. So the main conjecture I want to talk about is that there exists a function f such that if G has no odd hole, then the chromatic number is at most f of the clique number. So if you fix the clique number, then you have a bound on the chromatic number. And this is a theorem. So I'd like to prove that. I can more or less do the proof. The proof is, it's much easier than the proof of the strong perfect graph theorem. You know, you might think it's similar because the odd perfect graph, the strong perfect graph theorem, we're saying no odd holes and no odd antiholes and trying to get chromatic number equals clique number. Here we're just saying no odd holes and we're trying to get a relation between chromatic number and clique number. You think it might be similar, but it's not at all. The proof is much shorter and the proof is quite nice. We can actually do it in a lecture. Jarfash had more conjectures. So he conjectured that there is a function f such that if G has no hole of length at least L, then the chromatic number is at most f of L and omega. So now f depends on two parameters. And he conjectured that there is a function f such that if G has no odd hole of length at least L, then same thing. So this conjecture implies the other two. So it's really this conjecture we would like to do if we could, but we can't at the moment. So I just wanted to show you what we can do. Let's think about this for the moment. There's two inputs. If I want to look at special cases of this, there's the hole length L, and there's the clique number omega. And so you could fix L and ask, can you prove it then? Or you could fix omega and ask, can you prove it then? So in conjecture 3, if I put L is, say, 5, then we're just saying no odd hole at all. No odd hole of length at least 5 just means no odd hole. That becomes equivalent to conjecture 1. But I could say problem 3 with omega equals 3 or some. I mean, let's make a table. Let's say here's omega. Omega is 2, 3, 4, 5, 6, and so on. And here's L. L's odd, and it's at least 5. And we have a problem for every entry in this matrix. This is so another way to state this conjecture is if you have a graph with no odd hole or length more than L, at least L, and no clique of size bigger than K, then the chromatic number is bounded by a function of K and L. So for every entry here, we can have a problem. I mean, there's a special case we could think about. And well, omega equals 2 is No, O big equals 2 just means triangle-free graphs with no long odd hole. And that's an interesting case. So here we don't know the answer. And so what this column is done. That's the theorem. That's problem 1. But all the rest is still open, except this one. So I'll show you the proof of this, and then if there's time, I'll show you the proof of that. It's completely different. This is Alex, Scott, and me. This one is Alex, Scott, and me, and Maria. And then let me see how time goes. If there's still time, I'll show you another theorem as well that we proved with a similar method. But so let me get these two things done first. Okay, so I want to prove that if G has no odd hole, then the chromatic number is at most 2 to the 3 to the omega. Actually, we found a slight improvement. We can do 2 to the 2 to the omega, but the proof is a little bit harder, so let me not. I'll just do 2 to the 3 to the omega. And what will the proof be? We'll do induction. And we can we assume it's true for omega minus 1. We'll assume every graph with no odd hole and every graph H with no odd hole and with clique number less than the clique number of G has chromatic number at most some quantity n. Then what do we need to prove to make the inductive step go through? Then it's enough to show the chromatic number of G, if it satisfies this, is at most 48 n cubed, I think. Yes. If I just said n cubed, then you would see why the proof works. If I could prove the chromatic number of G, whenever you increase the clique number by 1, the chromatic number is at most a cube of what it was before, then this would follow. You increase omega minus 1 and the top, you're being cubed. So that would be correct. I can't prove that, but I'll prove that this is at most 48 n cubed. That's already good enough. Might not look good enough, but it is. The reason is that the base case, you can actually prove something a little bit stronger than this. You can prove that not only this is true in the base case when omega is small, but actually this is true with a constant in front, like 1/64 or something. And then the induction goes through just with this weaker step. But let's not worry about that. I mean, if I could prove this, it gives me something like that. And in fact, it does actually give me this. All right, so we need to do that. So let's keep track of our assumptions. So assumption 1 is G has no odd hole. 2 is chromatic number of H is less than n for every H with clique number smaller than G and no odd hole. And then we need to show chromatic number of G is at most 48 n cubed. And I'm going to adjust, so this is our current goal. I'm going to adjust these assumptions and adjust the conclusion as we go along. So I'm going to update this board. We'll get more assumptions here and the conclusion will change. So this is going to be operated on. It works. Well, we can assume the graph's connected. I mean, if I'm trying to prove here's my graph and I need to prove its bounded chromatic number, you can look at a component of it. It's enough to prove each component has bounded chromatic number. So we can assume it's connected. So I might as well add that as a hypothesis. If I want. Well, in the connected graph, you can choose a vertex and classify everybody else by distance. Right? These are the people distance 1 from that vertex. These are the people distance 2. So everybody here has a neighbor upstairs. Everybody here has a neighbor there. And so on. So I'm classifying people by distance. Now, if I could prove that each of these classes had bounded chromatic number, say if I could prove this had chi at most 24 n cubed, and that was true for each of these levels, then I've got 48 n cubed colors I can use. So I use 24 n cubed of them for the odd sets, and the other 24 n cubed for the even sets. And I can use a color here and the same color there because there's no edges between them. So if I could color each of these sets individually with 24 n cubed, then I can color the whole graph with 48 n cubed. Right? I mean, the whole proof is a succession of tricks like this. And so far, nothing is difficult in this proof. Let's call this a leveling. So this is L0, L1, L2, down to LK. So it's a sequence L0, L1, LK, where, well, I don't really insist it contains all the graph. It's convenient not to say it contains all the graph. So the definition of a leveling is that every vertex in Li has a neighbor in Li minus 1 and no neighbor in L0 to Li minus 2. So just that. And L0 is a singleton. So that's what I mean by a leveling. You start with a vertex, now you take some more vertices that have neighbors there, you take some vertices that have neighbors here but no neighbors there, take some more vertices with neighbors here and no neighbors earlier, and so on. And there may be vertices you don't even use at all. But that's what I mean by a leveling. So it's enough to prove that, okay. Let me get rid of this assumption and let me assume there is a leveling. So L0, L1 up to LK is a leveling. And then it would be enough to prove that the chromatic number of LK is at most 24. Right? I mean, I need to prove it for each level. But if I want to prove it for this level, just delete all, it's enough to prove it for the last level because you can make any level the last level by deleting all the other levels.
Are you assuming that this union of L's cover everything?
No, I don't need to. I mean, I only need it when the union of the L's does cover everything, but let's prove it more generally. I mean, if the vertices you don't cover, you could just delete them anyway. They don't make any difference. Now, all right, we got this picture. And I need to prove this set has chromatic number at most 24 n cubed. Right, now that's our goal now. Prove that. So what have I got all these other sets for? I mean, if I just look at this subgraph, it's a graph with no odd hole, no clique of size more than omega g. I mean, why is it better? I mean, aren't I just back where I started? I mean, I'm just trying to prove the chromatic number of this graph is bounded, but we know a bit more about it because we've got, every vertex here has a neighbor up in the next path, in the next level, and you can join them by kind of going up and coming down again. So, there are paths between them. That's some information. It's not much information, but it's something and it's helpful. Now, okay. I might as well. So the only function of these is to provide a leveling with that as the last set. So I might as well assume that everybody, say here, is needed for somebody in the bottom. If there's a vertex there that's not needed, if there's a vertex here and I could remove it and still I've got a leveling, then I might as well. Right? So we'll assume this is minimal covering that. And this is minimal covering that, and this is minimal covering that, and so on. Each level is minimal covering the next level. We might as well assume that. So what does that mean? If this, here are two consecutive levels, what does it mean that this is minimal covering that? It means that for every vertex here, you need it for something. If I remove it, then somebody here is not covered. So for every vertex there, it has a child, so that that child has only one parent. Right? If I remove that vertex, then this child won't have any parents. So let's call that the single parent property. So for each V in Li, there exists a U in Li plus 1. So for every V here, there exists a U there, such that V is the only parent of U. And this is true for all I, except for the bottom level. We need that I plus 1 exists. So I might as well assume we've got hypothesis 4, the single parent property. And prove the same conclusion. I'm not changing the conclusion. It's just an extra hypothesis. The more hypotheses I add, the easier the problem gets, right? It looks more complicated, but it's easier because you've got more hypotheses. If you don't change the conclusion, then life must be getting easier somehow. Now, what else can we do to simplify this? I might as well assume the bottom is connected, right? Because I only want to prove its chromatic number is small. If its chromatic number is big, it has a component with chromatic number big. So just delete everything else in the bottom. So I might as well assume LK is connected. Now, so look in a general level. And look at two vertices here, non-adjacent. If I just take two vertices here, there is a path joining them. This has a child. It has a child that it's the unique parent of, so it certainly has a child. And he has a child, and that has a child, so you can go all the way down to the bottom, and he goes all the way down to the bottom, and the bottom is connected, so you can join them up somehow. Now, maybe I want to get an induced path between these. So possibly when you make it induced, maybe that's an edge. That cannot be because he's got a unique parent. But maybe that's an edge, or maybe that's an edge. Perhaps you can shortcut. But somewhere there's a path between these in the bottom of the picture. And also there's a path between them in the top of the picture, because he does have a parent, and he does have a parent, and they both have parents. You can go up to the top if necessary. Somewhere they'll join, and then shortcut it to make it induced. So there's also a path between them at the top There's a path between them in the top and a path between the bottom. The union is a hole. It's a cycle, and it's induced, and its length is at least 4. It cannot be odd. There are no odd holes. That's the assumption. So that means that either this path is odd and that path is odd, or this path is even and that path is even. But in particular, either all these paths are even, or all these paths are odd, because they all have to be the same parity as that path. Right? So let's call that the parity property. That for all uv in Li, every induced path between u and v with interior in the top has the same parity. So either all these paths are even or all these paths are odd. And, I mean, it's true even if they're adjacent, because then there's only one path. There's only one induced path, but it's odd. So I might as well assume also, except I need to move the hypothesis down, but I'm not going to change it, I'm just going to move it down. 24n cubed. I might as well assume G, the parity property. Notice the parity property is not true in the bottom. It's true for any pair of vertices in Li as long as Li is not the bottom layer. Because I need to be able to go down and join up, and I can't go down from the bottom layer. So the parity property just says for any two vertices in any level different from the bottom, all paths between them in the top of the picture have the same parity. Okay, so far we didn't do anything very much, right? Now, okay, let me clean up the picture a bit. Now, choose a vertex here, and choose a child of it. Now that child has a child that it's a unique parent of. And that has a child that it's a unique parent of. And you can go all the way down to the bottom. So what does it mean? At every stage, all these vertices have unique parents. So they have no neighbors higher up, apart from the one you can see. Right? So you can do that. Let's call this path S. It's a spine, or it will be a spine. Now, let me look at how can people attach to the spine? If I look at a vertex out here with neighbors in the spine, what can it do? So here's the spine, and here's the general vertex. It can only be adjacent possibly to that, possibly to this, possibly to this. It can't be adjacent to vertices further down or further up, because there are no edges between this level and that level, or between this level and that level. Edges only go between consecutive levels or inside a level. So the only possible edges coming out of here are there, there, and there, and not there, because there are no edges going downwards. So the only possible edges are that. And so you get three kinds of vertices. There are vertices that look like this, there are vertices that look like that, and there are vertices that look like that. Except it's helpful also to break them by parity of their height. So I really want to say there's 6 kinds of vertices. So these 3 kinds, but I want to say that one is different kind from this one. So we'll have people of these three kinds at even height and people of these three kinds at odd height. That's 6 kinds. Now choose a kind. Let's say, I don't know, let's pick the triangle kind. So say, let me just keep all the vertices that attach on triangles at odd height. So people that do this, say. And now, for every vertex in the bottom, I mean, it has a parent, and that has a parent, and that has a parent, and you can chase it up until the first time you get to a vertex with a neighbor in the spine. Chase up the parents to the first time that you get to a vertex with a neighbor in the spine. It might not be one of these types. I mean, it's one of the 6 types, but it might not be this type. But do that, and let's look at the vertices such that the first vertex they hit is of this type. So that will divide the bottom into 6 sets. Right? There's the vertices so that when you take your path up, the first thing they hit is one of these triangle people at odd height. There are vertices so that as you take your path up, the first one they hit is a horizontal person at even height or something. I mean, there's 6 possibilities. And that divides the bottom into 6 sets. So, well, not disjoint sets, but it doesn't matter. You get 6 sets with union in the bottom.
When you go up,
you have choices that
right.
Doesn't matter. Just pick a path. We're assuming the bottom has got big chi. We can assume the bottom is big chi. That means one of these 6 sets has big chi. You know, because if they all had small chi, then the bottom would have chromatic number 6 times as much at most. So if I could prove each of these had chromatic number at most 4 n cubed, then the whole thing would have chromatic number at most 24 n cubed, and that's what I want. So let me assume there is a spine, and then I need to prove that for each of the 6 types, the people that descend from it have chromatic number at most 4 n cubed. So that for each of the 6 types, the descendants in LK of that type have chromatic number at most 4 n cubed. That would be enough, eh?
What's the type of the vertex in the spine?
Don't give them. It's only one vertex. They don't care. I mean, you can handle it, but there's only one vertex anyway. It's not going to make any difference. All right. So let's focus on one type, and let's prove that that set has chromatic number at most 4 n cubed. Let's delete all the others. And that means I can delete everybody up here. You know, all the attachments to the spine not of that type, and I'll just take just keep the people that are of this type when they attach to the spine, and keep their descendants. So we can assume there is a spine, and there is a spine S, and all vertices in the neighbors of S have the same type, just by deleting all the others. And we'll delete everybody in the bottom. Now we have to do LK. We need to show chromatic number of G restricted to LK is at most 4 n cubed. Because if we just delete all the other vertices, we're focusing on one type and their descendants. And now we can say that type is the whole of the bottom. Well, Oops, yeah. Except I cheated you a bit. I mean, there's a problem. What about this type? What would happen if I just keep the people of that type? So here we go. Take that spine. Now we keep the people of, say, that look like this. And we keep all the people that descend from them down the bottom. We're taking, so everybody here descends from one of these people that attaches horizontally. It's not a layering anymore. We messed it up. Because these guys don't have parents anymore. They might not. I mean, everyone else has a parent. Everyone else, you can still chase him up until he hits one of these horizontal people. But the horizontal people might not have parents. So we have to be careful now. We might have spoiled the property that it's a layering. Just throwing people away like this is a bit dangerous. But actually it's not. Because look, in this case, what you do is you take the spine and you move it up. And then you've got a layering again. move this vertex to that set, move this vertex to that set, move this vertex to that set. Just move every vertex of the spine up one notch. And then it becomes a layering again. No cheating. That's a good trick.
You change the first vertex?
Yeah, the first vertex goes up here. goes to one level higher, I guess. I mean, if you like, you can think of moving everybody else down a level instead of moving the spine up a level, whichever you think is easier. So we can assume all the vertices in NS have the same type, and it's not this horizontal type. So everybody on the spine, it might look like this, or everybody looks like that, or everybody looks like this. But in particular, everybody that attaches to the spine has a parent in the spine. So still, we're okay with parents. Now, why was that a good thing? Why did we do that? Let's go back to this picture. Well, let me choose a vertex here, some general level. Choose a vertex here. I mean, it has a parent, that has a parent, that has a parent. Eventually I get to someone with a neighbor in the spine. Then I go to the spine and I come down, 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 until I'm back here. So for every vertex you can go up until you get to a vertex in N of S, and then you come down the spine. Right? You get some, and that's an induced path, because you go up here to the first vertex that has a neighbor in the spine. So, so that means this is induced. Now, and for every vertex, no matter where you start, all the paths you generate this way have the same parity. Because you can see this one is odd, because the number of times I go up is the same as the number of times I come down, plus there's one extra here. So if I'm doing the triangle type attachment, then all these paths are odd. If I'm doing this kind of attachment, then all these paths are even. No matter where you start and no matter how high they go, they all come out to be even. So the path from any vertex going over to the spine and down again, all those paths have the same parity. And that's a good thing. Let me show you why. Because look at an edge here. I claim for every edge, its two ends have the same parents. For every horizontal edge, its two ends have the same parents. Because suppose there's somebody that's a parent of this and not a parent of that. Now there are cases, these guys might have neighbors in the spine, they might not. I'm not going to do all the cases. Let me just do the case when neither one of them has a neighbor in the spine. All the other cases are similar. So assume neither one of them has a neighbor in the spine. Well, he's there for a reason. He has a child with a unique parent, and I can chase that down to the bottom and go back up the spine. So there's an induced path in the bottom of the picture between these. And the important thing about it is that that vertex has no neighbors in there. Right? Why does it have no neighbors? It's not adjacent to that because this vertex had a unique parent. It's not adjacent to that because that vertex had a unique parent. It's not adjacent to that because we're assuming he doesn't have a neighbor in the spine. So this is an induced path. And going along there, it's still induced. But now I can do my trick, do this in the top, and I get a, well, is that a hole? There's a danger that he might have neighbors on the top, but he doesn't, because that's a non-edge, and he can't be adjacent to anything else. Or I could just go up from this and down again. One of those is odd and one of them is even. Because both, this path and that path have the same length mod 2. And the bottoms are the same, they're exactly the same. And one I've got this extra edge. So one of those is an odd hole, and you can't have an odd hole. Contradiction. So we just proved that for every horizontal edge, its two ends have the same parents. I didn't do all the cases. As I say, you have to worry about the case when one of the ends has a neighbor in the spine, or maybe they both do, but it's not hard. Let's call that the parent rule. So every horizontal edge, the two ends have the same parent. For every horizontal edge, UV, U and V have the same parents. And that's a powerful fact. From now on, I don't need, there are many things I don't need. I don't need the spine anymore. We can forget that. We just need the spine to prove the parent rule. So from now on, we won't use it. And we don't need the single parent property. We just, I think, yeah, that's right. I'll put them back. We could have them. They're true. We're just not going to use them anymore. So I'm erasing them, but carefully, in case I forgot. But I think I don't need them anymore. Now, where did we prove the parent rule? We proved it for edges in LK minus 2. The proof doesn't work for edges here. It doesn't work for edges in LK minus 1. The parent rule might not be true in LK minus 1. Why? Because, what did we do? What was the argument? We said, suppose there's somebody which is a parent of that and not a parent of this. I need a path from that vertex over to here that doesn't go through any neighbors of that. But how do I get that? He has somebody in the bottom that he's the unique parent of, but then I need to get from here over to there without going through any neighbors of that. And you can't do it in the bottom. If you have two layers, you go down 2 steps and then you're safe. You don't pick up any neighbors of him. But if you have to go out now, he could have neighbors further on this path. We don't know. So the argument doesn't work right at the bottom. It doesn't work in LK and it doesn't work in LK minus 1. But it works in higher levels. Okay. Here's LK minus 2. Here's LK minus 1. And here's LK. So our goal is to prove the chromatic number of LK is at most 4 n cubed. And we've got all those hypotheses now. Okay. Now, let me think what comes next. What goes on in LK minus 2? Let's look at LK minus 2. I claim it doesn't have a clique of size omega g. Because suppose it had a clique of size omega g. Suppose in here there's a clique of size omega g. Well, all these vertices, every two of these vertices have the same parent. So they'd all have a common neighbor up on the next level, and that would be a clique of size omega g plus 1. That's impossible. So when you have the parent rule in a level, that level does not have any maximum cliques. And that means we can color this by induction. We can color it with n colors. Yeah?
Is it because you have somebody with a unique parent? Or
No, just it's because of the parent rule.
parent rule says that for any pair you share at least one.
No, it says they've got exactly the same parents.
Oh, okay.
Parent rule says for any two adjacent vertices in the same level, they've got exactly the same parents.
As a set. We might have many parents.
Yeah, but yes. But every vertex that's a parent of U is also a parent of V, and vice versa. So that means that we can color that with at most n colors, because that's our assumption, that's what n is. Now, if you don't mind a little twist, let me show you can do better. Because you remember what cographs are? The graphs with no 3-edge induced path. I claim this graph is not only, this graph is a cograph. Why? Because suppose it had a 3-edge induced path. Well, all these vertices have a common neighbor on the next level. So there's a vertex up here joined to all of them by the parent rule. But I can chase this down and chase that down and join them up in the bottom. So there's an induced path like this. Not going through any neighbors of him or not going through any neighbors of... So these guys have no neighbors there. Well, now take that path. I can make a hole by going this way, or I can make a hole by going that way. And they're different lengths. One is one longer than the other, so one is odd. Contradiction. Can't have an odd hole. So, in fact, you can't even have a 3-edge path here. This is a very trivial graph. It's just a cograph. And that means it's not only n colorable, it's actually omega g colorable. You know, it's perfect. Its chromatic number equals its clique number because it's a cograph. So we can actually do better than this. And I told you at the start, you know, I'm proving 2 to the 3 to the omega. And I told you we could in fact do 2 to the 2 to the omega. Well, if you use that extra twist, it gives you 2 to the 2 to the omega. But it's another line, one line of proof. So if you want to ignore that, you can. Anyway, let's just use this chromatic numbers at most n here. That means I can partition it into n stable sets. So do that, and look at the descendants of each stable set. So partition this into n stable sets. So this is n stable sets. And look at the people that descend from the first stable set, look at the people that descend from the second stable set, and so on. If you could prove each of these had chromatic number at most 4n square, then the whole bottom would have chromatic number at most 4n cubed, and that's what we need. So in other words, I can assume, I'm going to move it down again, so I need a 9 that Lk minus 2 is stable. I could assume that, but then I have to prove something better. I have to prove 4n squared. And if I could prove that the descendants of each of the stable sets was colorable with 4n square colors, then since there's n stable sets, that would be 4n cubed total. That's what I want. All right, good. Happy so far? And here's LK minus 2. Here's LK minus 1. Here's LK. And this one is stable now. Can we get LK minus 1 to be stable? Well, what's its chromatic number? It's either big or small. I mean, let's forget LK for the moment. Let's prove the chromatic number of LK minus 1 is small. I mean, so that's our original problem, where we can assume this set is stable. Right? I mean, forget LK. Let me say I want to prove that the chromatic number of this is small. That's the same, I mean, it doesn't matter what K is, it's supposed to be true for all K. So that's the same as saying, proving that this has small chromatic number if this is stable. Well, so suppose I could prove that if LK minus 1 is stable, then this has got small chromatic number. Then it would follow that LK minus 1 has small chromatic number, in this, starting with that set being stable. So this has small chromatic number. And now you look at the descendants of each of these. And now I could prove that that is stable because its parents are stable. That has small chromatic number because its parents are stable. I'd have to multiply whatever my constant was. So if I could prove that this set is 2n colorable, then I partition it into 2n sets. And then for each of these sets, I look at its children. Similarly, I can prove that that's 2n colorable because its parents are stable now. And that's covered the whole bottom with 4n square stable sets. So that's colored the bottom with 4n square colors. So in other words, I can change this to LK minus 1 being stable, but now I have to update it again. I have to prove 2n instead of 4n squared. Right. Okay. So we're down to LK minus 1 and it's stable now. And I worry about the chromatic number of LK. Let me tell you what is the graph of jumps. If you look at any two vertices here, you can join them by an induced path in the top. Because each of them has a parent, and you just go up until you join up, and then you make it induced. And you can also join them by an induced path in the bottom. Because they're needed for someone, and they all have children, so you can go down to the children and join them around. And that means this path and this path have to have the same parity. Well, we got the parity property. We already proved the parity property. So for every two vertices here, all these paths are even, or all these paths are odd. Let's make a new graph where I say this is an edge if all these paths are odd. So there's two kinds of pairs. There's pairs where all the paths are even and pairs where all the paths are odd. Let's look at the graph of pairs where all the paths are odd. I call that the graph of jumps. So it's a graph with vertex sets LK minus 1, where we say U is adjacent to V if all paths, all induced paths between U and V with interior in the top, if all such paths are odd. So once again, they're either all odd or they're all even. And let's define some graph on this set. It's a different graph. I claim it's a cograph. Let's call this graph of jumps J. So this is the, I mean, so far all we did was kind of just simplifying the problem and hoping something good would happen. We didn't yet do anything clever. We just simplified it. And now this is the kind of magic lucky bit that makes the proof work. That the graph of jumps is a cograph. Why is that true? Well, suppose there were 4 vertices here, so that, that's an edge of the graph of jumps, and so is that, but the other 3 are not. So, in other words, if I look at a path like this, it's odd, but if I look at a path like that, it's even. And so for each of these 6 pairs, I know the parity of the paths. Well, this vertex has an ancestor, and you trace it up to the top, and this has an ancestor, you chase it up, this has an ancestor, you chase it up, this has an ancestor, chase it up. Let's look at the middle 2. When do they first hit each other? This has a path, and that has a path. I know that when they meet, the induced path I get between them has got to be odd, because that is an edge of the graph of jumps. So how can they meet? And they can't meet like that, because then you'd have an even path. They have to meet, the first time they meet must be a horizontal edge. So if I go up the middle, then the first thing that happens is a horizontal edge. And now, well, what happens if you go up the side? Eventually, is it possible you just miss this part? You don't have any chords over to this part at all? Let's suppose you just miss. Well, you've got the parent rule here. This edge has a common parent in the next level. And so just go up and go up from here until they meet somewhere. I don't care if that path is odd or even. But now I get an induced path like this. And I could come down that way, or I could come down that way. They're both induced paths, the same length, and yet one is joining this odd pair and one is joining an even pair. So that's impossible. So you can't miss. If I follow this up, it has to have a chord to that section. And you look at the first chord, wherever it is. And similarly for this one, you look at the first chord, wherever it is. And now you have to do cases. I mean, this is I guess the hardest proof in the paper. It's like 2-3 pages. You have to go through all the possibilities for how high do you go on the side paths. But it's not hard. You just have to enumerate the cases, and they all work. No, I mustn't erase that. That's vital. So it's a cograph. Now, nice thing about cographs is there's structure theorem for cographs. So if you have a cograph, then it's either disconnected or its complement is disconnected. So what do we want to prove now? I'm going to forget all these higher levels. We're just going to look at LK minus 1 and LK. If I look at 2 vertices here, you get this, and look at paths below. They have the same parity as the paths above that used to join them. So I can still get the graph of jumps by looking at paths below. Same graph, it's still a cograph. So from now on, I'm just going to look at these 2 levels and prove that this is 2n colorable. Well, actually, I'm going to prove that you can 2-color the vertices so that every maximum clique gets both colors. Let me say that. I claim you can partition L of k into x and y such that every omega g clique in LK intersects both x and y. If that were true, then look at x, it does not include a maximum clique, because every maximum clique has a vertex in y. So that means you can n-color the vertices in x, and you can also n-color the vertices in y, so that's 2 n-colors. That's what we wanted. But, so it's enough to get a 2-coloring with this property. And then you just prove by induction on, you look at this cograph and do induction on, let me show you the argument. So once again, here's my cograph, and here's LK, and we want to prove that you can 2-color the maximum cliques here. So now there's 2 cases depending whether the graph on the cograph is disconnected or its complement is disconnected. Let's suppose, let's say it's disconnected. So say it's, the graph of jumps is disconnected. So that means if I choose every vertex on the left and any vertex on the right, all paths between them don't give me edges of the graph of jumps. All paths between them are even. So let's say all these paths are even. For every vertex here and every vertex there, every induced path between them is even. Case 1. Well, so actually let's do the other case first because it's a bit easier. Let's do the case when all these paths are odd. Now, I'll do both, but let me do the odd one first. So, well, that means in particular, if I look at it, every vertex here has a neighbor in the top. It can't both have a neighbor on the left and a neighbor on the right, because that would be an even path between 2 vertices, between a vertex on the left and a vertex on the right. Right? So, the bottom gets partitioned into 2 sets. There are people with parents here and people with parents there. And nobody has parents on both sides. There can be edges across, but no, the vertical edges just stay on the left or stay on the right. Now, well, inductively, if I take that set and this set, I can 2-color the maximum cliques contained in here, just by induction. And I can 2-color the maximum cliques that are contained in here. We worry about the cliques that leak across. What about cliques that leak across? Well, you can certainly 2-color the cliques that meet both sides. Because if there's a clique like this, you color this side white and that side black. Right? So for the 3 kinds of cliques, there's cliques completely on the left, cliques completely on the right, and cliques that meet both sides. You can certainly 2-color each kind. The problem is they might overlap. Your colorings might interfere, because maybe there's a clique completely on the left that intersects a clique that leaks across. So what would that mean? Maybe there's a clique completely on the left and a clique that leaks across that intersects it. And then you wouldn't know how to color that vertex. Do we color it according to the rule for coloring cliques on the left, or do we color it according to the rule for coloring the cliques that meet both sides? I mean, if they intersect, our method doesn't work. But let's prove that this can't happen. You can't, if I take a clique on the left, you can't even have a neighbor on the right. This already is impossible. That's an omega G clique. Let's prove that this is impossible. You can't even have a neighbor on the right. Because suppose he does. Well, let's look at all the vertices adjacent to this guy. It's not everybody, because that's already a maximum clique. There has to be a non-neighbor here. Look at the parents of these non-neighbors. All the people joined to those non-neighbors. And look at a parent of him. I mean, I can try and go 1, 2, 3, 4, and try to get an even path. There are no even paths like that. But the problem is that path might not be induced. The only place it cannot be induced is maybe this vertex is adjacent to that vertex. So it must be, because otherwise I have an even induced path between left and right. So all of these vertices are adjacent to all of those vertices. Well, if I take a vertex here, it's not adjacent to the whole of this maximum clique because it's a maximum clique. So everybody here has a non-neighbor, has a neighbor and a non-neighbor in this set of leftovers. So choose somebody joined to as much of this as possible, and he's still got somebody he's not joined to. So choose somebody else joined to that, and he's not joined to one of these because I already chose the one with his most neighbors, and it gives me a 3-edge path between them. What's wrong with a 3-edge path between them? You can't have a 3-edge path between them because that means this is an edge of the graph of jumps. That's an odd path. But I can see an even path joining these. You go that way, by that vertex. You can't have a 3-edge path and a 2-edge path joining the same two vertices. So that's the proof in the case when the cograph is disconnected in the complement. Let me do the proof. I was going to do 3 theorems today, and this is still the first. I'm nearly there. Let me do the proof when the cograph is, the other case, when the cograph is disconnected. So now all these pairs are even pairs. Well, so now you can have people, there are people that only have parents on the left, there are people that only have parents on the right, and there are people that have parents on both sides. It's now possible. You can have even paths. Where are the maximum cliques on the bottom? There can't be an edge from here to there, because that would give me an odd path between left and right. So there are no edges like this, but there can be edges here and there can be edges there, but there's no edges going a long way. So where are the maximum cliques on the bottom? They can be in here, or they can be over there, but they can't meet both this and that. So you've still got two kinds of cliques in the bottom, the sort of left side cliques and the right side cliques, and I can color these. I can color because they're children of that, and the cliques in here I can color because they're children of that. So I'm just applying induction on the size of the cograph. And again, the problem is maybe they overlap. Maybe there's a maximum clique like this and a maximum clique like that that shares a vertex. And we need to prove that's impossible. And the argument for that is, it's basically the same, except I've forgotten what it is, just a minute. Suppose this is an omega clique contained on the left, so everybody here has a parentum in that set, but it has a neighbor, but also one of these vertices has a neighbor in that set. Let's prove that that's impossible. And if that's impossible, then our two sets of cliques don't overlap at all and we can color them independently. Let's prove this is impossible. So exactly the same argument. Look at all his neighbors. He's not joined to everybody. Now you look at the parents of these guys. They have to be complete to this set, because otherwise I go 1, 2, 3 and get an odd path from left to right, and all paths left to right are supposed to be even. So once again, this set is complete to that set. So these are not complete to that set, so you can get a 3-edge path here, but I've also got a 2-edge path. Contradiction. Same argument as before. So it's nice and easy, that cograph lemma. Just works nicely. And what am I done? That's the end, right? That's the end of the proof. Right? This enormous thing has actually come out. All right, so let me... any questions on it? I'm not going to change theorem and show you the proof of a different theorem, but that's the end of the theorem about odd holes.
So, can it be improved to less than double exponential?
I don't know. I mean, maybe. I mean, we have a lower bound, which is, there is a graph with no odd holes with chi at least omega to the 1.2 or something like that. Not very much. I mean, I forget the exact number, but it's something like 1.2. I mean, that's the best I know. I mean, maybe this is the truth. Maybe you can color. You can always color without many colors. I don't know. Okay, let's go back to Scharfascher's general conjecture, where you're assuming there's no big clique and you're assuming there's no long odd hole. No odd hole of length more than L. And again, you want to prove the chromatic numbers about it. So there might be short odd holes. And I want to do the case, so it was open even for triangle-free graphs. So let's assume that the graph is triangle-free. And we'll assume G is triangle-free and has no odd hole of length bigger than 5. And then the theorem is, we'll prove the chromatic number, well, it's not a function of clique size anymore because there are no cliques. We don't have any triangles. I mean, the biggest clique is only size 2. We'll prove the chromatic numbers, I wrote it down, I think it's 82,000. 82,000, yeah, 82,200. I mean, as far as I know, they might all be four colorable. I mean, I suspect this is actually true, that they're all four colorable, but I don't know how to prove it. So we're saying there's no induced odd cycle of length 3, and there's no induced odd cycle of length more than 5. So what we're saying is all induced odd cycles have length exactly 5. Every induced odd cycle has length exactly 5. Let's call the graph pentagonal. Every induced odd cycle has length 5. I mean, it's a kind of odd concept, but such graphs exist. So for instance, the Peterson graph has this property. Every induced odd cycle in the Peterson graph has length 5. Or the graph which I always thought was the Michelski graph, but it turns out it's not the Michelski graph, it's the Grutch graph. That has is pentagonal. So the following graph, you take a pentagon, and it's helpful to draw it like this, and you make a, so for each vertex you make a copy of it, which I'll draw on the outside. And then you add another vertex joined to all these new vertices. This is the, except I can never spell Grutch. How do you spell Grutch? T-S-Z... I wrote it down. I wrote down these things that are important things. T-Z-S-C-H. That's the Grutch graph. And this is not three colorable. So that proves at least that not all pentagonal graphs are three colorable, but that's the worst graph we know. Maybe they really are all four colorable. Well, so what can we do? Let's do the same thing we did for the odd holes proof. Let's start with a leveling. We might as well assume the graph's connected. We'll take a leveling. And it's enough to prove chromatic number of LK is, I'm not going to bother with the exact numbers. If I could get a bound on the chromatic number of LK, then the whole graph would have chromatic number at most twice as much. So is it most constant? It would be enough to do that. Now let's do all those tricks with spines and parity and all those. Let's do exactly the same stuff. The spine argument still works. I mean, we might as well assume this is connected. We might as well assume this is minimal covering that, and this is minimal covering that, this is minimal covering that. So you've got the unique parent property. Why not? So you can choose this path coming down. And now, how can you attach to the spine? Well, you can't attach with a triangle anymore because there are no triangles in this graph. So life got a bit easier. You can attach horizontally, or you can attach slopely. And that's all you can do. And so look at the people down here that descend from the horizontal attachments and the people down here that descend from the slopey attachments. One of them has to have big chi, or else the whole union has small chi. So another factor of 2 there. It's enough and if it's the slopey attachments, again, do our trick, move the spine up 1 notch. Sorry, if it's a horizontal attachment, you do the trick and move the spine up 1 notch. So you can assume every vertex in N of S attaches as, like this. It's got a neighbor, attaches like that. All right. Now, let's try and get the parent rule. And you can. That argument still works. Actually, that argument for the parent rule, if you do it carefully, you don't need that there's no odd hole, you just need that there's no long odd hole. Even if there are triangles, it still works. Yeah, it still works, even if there are triangles. You can still prove the parent rule, just assuming there's no long odd hole. I think since I'm running out of time, let me not do that. But you can still get the parent rule. Now here, what's the parent rule mean? You can't have the parent rule if there are no triangles. Well, that means all these sets are stable. There's no horizontal edges. No horizontal edges at all inside these sets, because that would have to be a triangle if you have the parent rule. So all these sets are stable down to LK minus 2. And now, by our usual trick, it's enough to prove LK minus 1. So for LK minus 1, its parents are stable. If I could prove its chromatic number is small, then repeat and try and get a bound on LK. Shouldn't be doing that step. That's a wasteful step. Anyway, the point is, I've forgotten the argument. For some reason, you can get LK minus 1 to be stable as well. Lost it now. Why is that true?
Wasn't it like if you prove that LK, I mean, we knew LK minus
So what we did before was we said if this is stable, then if this has got small chi, I'll just take for each color class, I'll take its children. And if it's got big chi, I might as well just look at that set anyway and forget that set. But you can do better than that. Do you remember what it is? Fortunately, I've got a co-author. Anyway, let me not worry about it. So I can.
You just look at a nation that's set and round it upwards.
Anyway, I guess it's good enough to say, to do what we did for the odd holes proof. We can make this stable as well. So you can get this stable layering. It's a layering where all the sets are stable except for the last layer. And that's a key lemma. You can, so in any pentagonal graph, you can get this stable layering. Right, so suppose I've got a stable. It's enough to prove that if all these layers are stable, then this has got chromatic number at most constant. It'd be enough to prove that. Well, So what can be, let's just think about what can be here. I mean, it's a pentagonal graph, but that pentagonal graph, I mean, the Michalski, the Grudge graph was pentagonal. You can prove that this cannot contain the Grudge graph as a subgraph. Because you just assume it's present, and then you ask how can it be covered. You know, you've got 11 vertices here making the Grudge graph. Each of them has to have a parent somewhere, and you look at the possibilities of these, and it's not so hard. It takes a page and a half to go through all the cases. It's not really difficult. The point is, for every two of these, you can join them by an even path on top. Remember, all these layers are stable, so every path now between two vertices here is always even in the top. So they can't be joined by an odd path in the bottom of length. I mean, pentagons are okay. I have to get an odd hole of length at least 7. Sorry, I'm doing this too fast now. I've half forgotten the proof, and I'm rushing anyway. But you can prove there's no Grudge graph here. You just have to stare at it and prove it. Well, all right. So now forget the layering. It's enough to prove that if you've got a pentagonal graph that doesn't contain the Grudge graph, then its chromatic number is small. It'd be enough to prove that, because you apply it to this subgraph. All right, so now let's suppose this whole graph now has no Grudge graph. And again, let's start doing a leveling. So we can get our stable leveling. And now what can you say about here if the whole graph doesn't have a Grudge graph? Now you can prove inside here, if I look at a vertex and I look at its neighbors and look at the second neighbors, that this set has bounded chi. The second neighbors of any vertex in the bottom have bounded chi. Now that's a big step, because the way you normally prove the graphs that the second neighbors of a vertex have bounded chi is you use the fact there's no pentagons, and all this graph has is pentagons. It's the opposite of, you know, this is a graph that's full of pentagons. It doesn't have any other kind of odd hole. So it was a challenge to do the chromatic number of people at distance 2 from a vertex. I mean, I could show you the argument for that, but let me not. Let me try to get to the end of the proof instead. So suppose you knew that. So that means now it's enough to prove if G is a pentagonal with no Grudge, and for every vertex, the second neighbors of V have bounded chi, then chromatic numbers are mostly constant. Well, all right, so let's try and prove this statement. Now, take a leveling, so we can take a stable leveling. And now, down here, you can prove that the third neighbors of every vertex have bounded chi. It's not going to go on. We stop at third neighbors. Third neighbors is enough. Don't worry. So that means I can assume that for every vertex, the third neighbors of V have bounded chi. I mean, this whole trick is you take a leveling and you convert it to a stable leveling, and now you look at that subgraph, and in here you take a leveling and you convert that to a stable leveling, and you look at this subgraph, and now inside here you take a leveling, you convert it to a stable leveling, and you look at a level. You keep taking nested levelings inside levelings, and the further you go, the more restricted the graphs get. Anyway, so we can assume all this. Now what? I mean, we only know one trick. Take a leveling, convert it to a stable leveling. Here we go, here's a leveling. And we've got all these properties now. Well, suppose the bottom has got huge chi. suppose this has got huge chi. We can assume everybody else is minimal covering the bottom. So choose a vertex there and come down till you hit the bottom. Now, he might have lots of grandchildren. Let's take all his grandchildren. If I delete his grandchildren, this is just distance 2 from that. So these have bounded chi. The bottom has huge chi. So if I delete that set, I've still got huge chi. So out here, there's still huge chi. Not quite so huge. Not quite so huge, a little bit smaller. And so there's a component out here. When I delete these vertices, there's a component out there with huge chi. Take it. And we can assume there's a component here with huge chi. It's connected with huge chi. And one of these vertices has a neighbor there. Because the bottom was connected when we started. Well, let's forget everything else. You don't need all this stuff anymore. I just want to pass down to that and get into there. Now, he's got a parent. This is not adjacent to that because we've already listed all the children and grandchildren of that. And they didn't get that vertex, we only got this one. So that's not an edge. This is not an edge because these levels are stable. And that's not an edge because you don't have any triangles. So this thing is an induced path. Okay. Now, where are the people at distance 3 from that vertex have bounded chi? And let's look, where are the people at distance 3 from that? There are some subset of this. So if I remove them, I've still got huge chi. Distance at least 4 from this vertex. All right. So come down here to a child with a neighbor in there. It might be the same as this guy. Doesn't matter. Maybe it's the same, or maybe it's not. Doesn't matter. And now. No, these are people distance 3 from that. So I can't get there in one step, but choose a path down and a path across until I get there. I'm sorry, like that. And once you get there, go up. Now, what can happen? What chords can you get? This is not adjacent to that because this level is stable. This is not adjacent to that because some reason. Oh yeah, this is distance 3 from that. Distance 4. That can't be an edge because this is distance 4 from that. So that can't be an edge. So this doesn't have any neighbors there. Well, so we know what this path is even. Why is it even? Because I can join it that way somehow by an even path. And it would be long. It would be at least 7, so it has to be even. So this bit is even. Well, let's do it differently. Come down, go along there, and now go down this. And now join it up. And what have I done? I've added 3 more edges. So if it used to be even, it's become odd. And it's got even longer. I had to be careful I didn't pick up any chords. Well, he doesn't have any chords here, we already said, and he doesn't have any chords there. So all I have to do is join it around the top, and you can. And that's the argument. So once you get distance 2 bounded chi and distance 3 bounded chi, then suddenly it all becomes easy. But you have to do these iterated levelings inside of levelings to get distance 3 to be a bounded chi. And once you've got that, then it's easy. But anyway, okay, let me stop there. Thanks.